We are going to discuss about complex numbers. We'll re-look at all that we have done. Look at the three forms in which we can represent complex numbers and then go ahead. So the first idea is that every complex number is made up of a real part and an imaginary part. If we think of the same plane as a coordinate plane or a Cartesian plane where we used to have an x and a y axis, now in the complex number domain we have a real number plane and an imaginary number plane. So any number now, so we are expanding our domain beyond real numbers. So real numbers belong to complex numbers. That means complex numbers is a bigger family than real numbers, correct? So any complex number is made up of a real part and an imaginary part. So this is A, this is B, and with respect to the origin, this number is A plus IB. It is not A comma B because A comma B is used for representing x and y coordinate of a number. It's called ordered pair. We do not write it as A comma B. We write it as A plus IB because that's how the representation is. This is called the Cartesian form of a complex number. And the variable z is used to represent the complex number. Same like we used to use x and y. We can also write z as x plus iy, where x is the real coordinate now, not the x coordinate, and y is the imaginary coordinate, not the y coordinate. What is this the variable I? I is standing for square root of minus 1. Why have we introduced this? Because the whole idea of complex numbers came from the fact that quadratic equations of this form did not have a solution in the real number domain. So we said x square equal to minus 1 is not possible in the real number domain. But now we are saying in the complex number domain, I can think of x square as plus or minus I. If x is plus or minus I will get x square as minus I. Right? Because if I is defined as square root of minus 1, then I square is minus 1. So that is the very fact from where complex numbers originated, that finding solutions for quadratic which did not exist in the real number domain. So the symbol I is a representation. It's not visually possible to think of an imaginary number, or like natural numbers, it is not possible to count. Okay. Now, in addition to the Cartesian form, we also saw that every complex number can be thought of as the distance that it takes to move to come to A plus IB from the origin. So R is the modulus of a complex number and is given by the square of the real part plus the square of the imaginary part. What is the name for it? It is called modulus of the complex number. It is same, if you pay attention, it is same as the distance formula. We are using the Pythagorean theorem to get the modulus. The second part which defines it, modulus, because modulus only tells me how far I have to go from the origin to reach to the complex number. I also need the direction in which I have to go to the reach, because the number could have been in any quadrant. It could have been in the first quadrant, second quadrant, third quadrant, fourth quadrant. I could have gone the distance r in either one of them. So in addition to distance, I should also know theta. Theta is called the argument of the complex number and is defined as tan inverse imaginary part upon real part. Where has that come from? Again, if you pay attention to the diagram and your definition of trigonometric ratios, that's all you get. So this same number A plus IB can also be written as R angle theta, where R is the modulus, which is square root of A square plus B square, and theta is the argument. Both of them tell me the same thing. Pay closer attention onto the diagram. And let's see what this r and theta are really. If this is my complex number and this is r and this is theta, then how can we define this opposite side which is b? Well, opposite side is r sine theta and the adjacent side a is r cos theta. So that means the Cartesian form of the complex number can also be written as r times cos theta plus I sin theta. Yes, and it makes sense. That means a complex number has the radius r on a circle and the argument theta. If I'm changing r or I'm changing theta, I'm changing the complex number. Same like if I'm changing a or b. Now, so this is called the Cartesian form and the angle and modulus is called the polar form. We are going to look at the third form of the expression called the Euler's form of representing a complex number. But for to go here, we will have to rewind a little and understand the definition of E. So when we had defined this number E, which is also called the Euler's number, we had written something like this. Limit as n tends to infinity 1 plus 1 by n the whole raised to n. Instead of giving you an expression like this, let me explain what I'm saying. So I'm saying if I invest 1 rupee at 100% interest, 100% rate of interest, and I compound it n times in 1 year, then how much money will I get back? This is the amount of money that I'll get back. If I go on increasing n, if I go on changing n to compounding 4 times, 10 times, 100 times, 1000 times, as I go on increasing, that's what this limit as n tends to infinity tells me, right? Limit means in the condition, in the limiting condition that n becomes very, very large. Where else had we seen this symbol limit as n tends to infinity? If you remember in the asymptote, when we would say vertical asymptote, say for example 1 by x. 1 by x is the function. Limit as x tends to 0. What happens to 1 by x? 1 by x becomes infinity in the limiting condition. So that's the meaning of limit. Okay, when n becomes very, very large, the amount of money that this grows into is almost equal to 2.718 dot 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 dot, and this number is defined as E, which is the Euler's number. So effectively they say whenever I'm compounding any money, right, I normally write this as 1 plus r by k into n, isn't it? Where k is the number of times I'm compounding, r is the rate in percentage. So if you are wondering why I'm not writing r by 100, because that r by 100 is r. So instead of writing 5%, I'm writing it as 0.05. That's why I didn't put 100. So 1 plus r by k into n, where n is the number of years for which it is compounded. If this k goes on increasing, okay, becomes very, very large, the same expression for compound interest will become this, because the 1 plus r by k raised to k becomes e raised to r raised to n, because n is the number of years for which it is compounded. This is the importance of this number e. So pay attention on how we defined e raised to r. So we are saying this, the number e raised to r is a binomial expansion of isn't it? If you pay attention on this expression and this expression together, you will see that this is what is coming to e raised to r. If we follow our binomial expansion formula, what is e raised to r going to be? What is binomial expansion formula? Do you remember? It's NCR a raised to n minus r b raised to r. Well, a in this case is 1. A is 1. N is same as k. R is going from 1 till 0 till infinity. And b is this number r by k. So it is 1 plus k times kc1. kc1 times r by k plus kc2 times r by k the whole square plus kc3 times r by k the whole cube, and so on. When we expand, the k and k gets cancelled, 1 plus r plus k into k minus 1 upon k square into r square plus k into k minus 1 into k minus 2 upon k cube into r cube, and so on. When k becomes very, very large, that's what we want to find out, right? When k becomes very, very large, what happens to this? Look at the way I'm simplifying this expansion. And what am I left with? I'm left with 1 plus r. When k is very, very large, 1 by k, 2 by k, everything will become 0. So I'll get 1 plus r square plus r cube. Oh, also upon 2 factorial. Sorry, one more thing I forgot. NCR also has r factorial upon 3 factorial. And so on. So this is what is e raised to r. From this compound interest formula, this is what we derived. So e raised to r means exponential growth. And what is this r denoting? Well, here it is the rate. Or I can say it is growing for how long? Till r. Similarly, if I think of a complex number, any number is cos theta plus I sin theta. If theta changes, it rotates. As theta changes, it will occupy different places along this circle of radius, unity in this case, but it could have any other radius as well. So it is growing with an angle theta. E raised to r means growing till r. It is growing, but it is growing to an extent which is determined by r. Same way, if it is e raised to theta, it is growing to what extent? Till theta. As soon as I put an I in front of it, what does I always do? Multiplication with I means rotation. So e raised to I theta means rotating by till theta. It is growing, but it is not growing exponentially, it is growing angularly till it reaches theta. So e raised to I theta is starting from the real number domain. So it's starting from 1 and it keeps growing till it reaches theta. And that is same as the number cos theta plus I sin theta with radius as 1. So that means e raised to I theta and this cos theta plus I sin theta are essentially representing the same thing. What is e raised to theta? E raised to theta is representing growth till theta. But as soon as I put I in front of theta, it is representing growth, but it is representing growth angularly. So it is growing angularly till theta. Now any number, any real number growing angularly till theta will make it reach to a number which has cos theta as the real part and sin theta as its imaginary part if I am looking at the complex number domain. So that means this e raised to I theta should be same as cos theta plus I sin theta. This is what is called the Euler's form of representation. So if I substitute theta as pi, that means if I rotate it till pi, what do I get? E raised to I pi is cos of pi plus I sin of pi. Sin of pi is 0 and cos of pi is minus 1. E raised to I pi is equal to minus 1. This is called the Euler's formula. It is also called the world's most beautiful equation. The reason is E is an irrational number, 2.718 dot dot dot. I is an imaginary number, which is square root of minus 1. Pi is an irrational number, 3.141521 dot dot dot. But when I combine these three numbers, two irrational numbers and one imaginary number, what am I getting? I'm getting a real number minus 1, which has a fixed value. So mathematicians were amazed with the fact that combination of two irrational numbers and one imaginary number is leading to a number which has a definite value. That's the reason it was quite an astonishing fact for many mathematicians. So bottom line is every complex number has three forms of representation. A plus IB, which is called the Cartesian form. R theta or R cos theta plus I sin theta, which is called the polar form. And e raised to I theta, which is called the Euler's form. All the three are the same complex number represented in different forms. How do you find R? R is a modulus square root of a square plus b square. How do you find theta? Tan inverse of b by a. So this is what you need to remember throughout this chapter, that I can use these forms interchangeably depending on what kind of a question am I solving. Now, if R cos theta plus I sin theta is same as R e raised to I theta, then let me see what happens when I raise a complex number to a power. Okay, so z is raised to 2, for example. Then R cos theta plus I sin theta should also be raised to a power, and R e raised to I theta should always also be raised to a power. What happens when indices, laws of indices, what does it say? The indices get multiplied. So this should have become R square e I 2 theta. Okay, let's see what happens when I expand this. R square is correct and the bracket becomes cos square theta plus 2i cos theta sin theta minus sin square theta. Okay, cos square theta minus sin square theta is cos 2 theta and 2 sin theta cos theta is sin 2 theta. So these two are still the same. Look at this. I 2 theta and this is cos 2 theta, sin 2 theta. So the polar form and the Euler's form is still the same. So when I raised it to power, what happened? The modulus got multiplied and the angles got incremented by that same amount. Let's try one more thing. Let's try z cube. So z cube means my polar form will become r cube and this will become cos theta plus I sin theta the whole cube, and this will become r cube e raised to I 3 theta. Let's expand what is in the middle. R cube, what is a plus b the whole cube? It's a cube plus b cube plus 3a square b plus 3ab square. AB square. Okay. If I write, so I'll collect all the real terms together. So cos cube theta minus 3 cos theta sin square theta plus I bracket 3 cos square theta sin theta minus sin cube theta. If you write down the formula, we had done this when we did identities. We had found the formula for cos 3 theta and cos sin 3 theta. If you go back to that, you'll realize this whole expression is nothing but cos 3 theta. This whole expression is nothing but I sin 3 theta. You may try doing the expansion. You can change this cos square theta to, or you start from sin 3 theta and go to this. You will get the same result. So again, you're seeing that these two are the same. So in general, if I raise a complex number to the power n, my polar form will become what? This. And my Euler's form will become what? This. Can n be positive, negative, root, like a power or like a fractional root? For example, z raised to half. Will it work? Yes. Apparently, this theorem works for every single power. Because of, in the index form, it is very easy to see. If I raise the complex number to any power, the angle gets multiplied by that power. Very easy to see in the Euler's form. That's the reason the Euler's form is very, very useful. And what is this theorem called? This theorem is called De Moivre's theorem. What is the De Moivre's theorem? De Moivre's theorem says if a complex number is written in this form, then z raised to n is r raised to n cos of n theta plus I sin of n theta. So the modulus gets multiplied with itself n times and the angle gets added to itself n times. If you pay very close attention, this is like geometric progression. It is getting multiplied with itself r times. And angle is getting added to itself n times. So this is like arithmetic progression. Okay, so that's the De Moivre's theorem. And now what we are going to do is we are going to find out how can we use this concept of De Moivre's theorem for finding roots of unity. Okay, so roots of unity. What is unity? Unity is 1. So if I have a complex number 1, that means it has a real part, but it doesn't have any imaginary part. Imaginary part is 0. Can I write it as 1 plus I 0? The real part is 1, but imaginary part is 0. Can I also write it as 1 is the modulus and the angle is 2 pi, because cos of 2 pi is 1 and sine of 2 pi is 0. Well, yeah, tan inverse, or can I write it as cos of 2 pi k, where k is a positive integer, sine of 2 pi k. That means cos of 2 pi, cos of 4 pi, cos of 6 pi, cos of 8 pi, and so on. They're all 1. And sine of 2 pi, sine of 4 pi, sine of 6 pi, sine of 8 pi are all 0. So every 2 pi multiple of 2 pi, cos and sine values will remain the same. So I can write z as this. According to De Moivre's theorem, if z is raised to a power, the modulus also gets raised to the power, and the angle becomes this. So I'm going to use this to define roots of unity. So I'll say if n was half, that means what? I'm finding square root of 1. Well, you may say square root of 1 is 1. Yes, in the real number domain, I have only one square root is 1. However, in the complex number domain, let's see what it gives me. Z raised to half will be, according to De Moivre's theorem, it will be 1 raised to half cos of 2 pi k raised to divided into half plus I sine 2 pi k divided by 2. Where did I get this divided by 2? Because any number that is a power here gets multiplied, right? I'm sorry. It gets multiplied with the angle. That's what De Moivre's theorem is. So the number here n is half. So half gets multiplied with the angle. So that means the square root is cos of pi k plus I sine of pi k. And what values can k take? Well, k is a positive integer. Let me see. Let me put k as different values and see what happens. Let me start with k as 0. When k is 0, then the first square root of 1 is 1. Because cos of 0 is 1, sine of 0 is 0. When k is 1, what do I get? I get c2 as the other square root of 1 is minus 1, because cos of pi, I substitute k as 1, so cos of pi is minus 1, sine of pi is 0, I get minus 1. If I put k as 2, I will get back 1. And if I put k as 3, I'll get back minus 1, and so on. So 1 minus 1, 1 minus 1, that means there are two square roots of 1, 1 and minus 1. On the Argand diagram, where are they? Square root of 1 is 1 and minus 1. This is where they are. These are the two square roots of unity. Did you realize I had to substitute only k as 0 and k as 1? After that, it kept repeating. So I didn't have to do other values of k. I had to substitute only two values. Because it was two roots, I had to substitute two values. And I started with 0 and I went to 1. Can I start with 2 and go to 3? 2 and 3? Yes. By convention, I'm always starting with 0. Let's similarly find the cube root of unity. Cube root of unity. Again, what is the procedure? I write 1 as cos of 2 pi k plus I sine of 2 pi k. If I want to find cube root, then by De Moivre's theorem, modulus is also going through cube root, but the argument gets multiplied with 1 by 3. Now let me substitute k as 0. When k is 0, cos of 0 is 1, sine of 0 is 0, so I get answer as 1, the first cube root. I substitute k as 1, I get cos of 2 pi by 3. 2 pi by 3 means 120. So cos of 2 pi by 3 is minus half. Sine of 2 pi by 3 is root 3 by 2. So this is my second root of unity. Well, if you pay attention to it closely, the modulus is real part square plus complex part, imaginary part square is still 1. So the modulus is 1. So the cube root of 1 is 1 in terms of magnitude. But the angle has changed. What is its angle now? Its angle is 2 pi by 3, which is 120. If I substitute k as 2, I will get the third cube root of 1, which is cos 4 pi by 3 plus I sine 4 pi by 3. Third quadrant, 240. Cos value is minus half, sine value is minus root 3 by 2. Again, if you look at the modulus, it's still 1, but the angle has changed to 4 pi by 3, which is 120. If I substitute k as 3, I'll come back to the same value as k equal to 0. If I substitute k as 4, I'll come back to the same value as k equal to 1. If I substitute k equal to 5, I'll come back to the same value as k equal to 2 and so on. That means after 2, it is going to repeat. So k equal to 0, 1, 2. 3 values are enough. Let me graph it and show you where these roots are. So the first root z1 was 1. The second one was minus half plus root 3 by 2. But at the same distance as 1, right? If this is 1, this also needs to be 1. So somewhere there. It is at 2 pi by 3 radians. Again, some 4 pi by 3 radians, which means again 2 pi by 3, I will be at the same distance of 1, but at minus half minus root 3 by 2. Okay, that is 4 pi by 3. So where are my roots now? If you join them, you will realize that the 3 roots are on an equilateral triangle. Okay, let me try the fourth root of unity. So let me go back and show you, okay, when I had square root of unity, I had 2 roots, a plus 1 and a minus 1. And again plus 1, minus 1, plus 1, minus 1. So I'm on a circle of radius 1 and I'm going on repeating. As soon as I did cube root of unity, I came on a equilateral triangle. But again this triangle is inscribed in a unit circle only. So this is an equilateral triangle inscribed in a unit circle. So I'm rotating still on a unit circle, but now I'll be going only at these 3 locations, which are the vertices of the equilateral triangle. If I do fourth root of unity, again what is unity? 1 can be written as 1 times cos of 2 pi k plus I sine of 2 pi k. What does 2 pi k indicate? All multiples of 2 pi. Cos and sine are periodic with 2 pi radians, so they will repeat in values. If I am taking the fourth root of unity, by De Moivre's theorem, the modulus gets also rooted, the angle gets multiplied. So let's find the roots by substituting k as, so if I substitute k as 0, I get the first fourth root of unity as 1 because cos of 0 and sine of 0. As soon as I substitute k as 1, it becomes cos of pi by 2 plus I sine of pi by 2. Cos of pi by 2 is 0, and so I get 1 times 0 plus I, which is I. K equal to 2, I get cos of pi plus I sine of pi, so I get minus 1. I put k as 3, I get minus I because I get 3 pi by 2. Cos of 3 pi by 2 is 0 and sine of 3 pi by 2 is minus 1. So I get minus I. After 3, if I put k equal to 4, I will get same value as 0. I put k equal to 5, I'll get same value as 1. K equal to 6, k equal to 7, and so on. So there's no point repeating any values of k now. So I got my 4 roots of unity. Where are my 4 roots of unity? It is at 1, then it is at I, then it is at minus 1, and then it is at minus I. And then it will repeat. So they are, by now you must have realized, they are on the vertices of a square inscribed in a unit circle. So again the roots are moving along a circle but on the vertices of a square. So we were on a circle, then we went on the vertices of an equilateral triangle, then a square, and now if you follow the pattern, you will realize the 5th root of unity will have values cos of 2 pi k by 5 plus I sine of 2 pi k by 5. If I substitute k as 0, I'll get 1. If I substitute k as 1, I'll get cos of 2 pi by 5 plus I sine of 2 pi by 5. What is 2 pi by 5? 360 divided by 5 is 72. If I substitute k as 2, I'll get cos of 4 pi by 5, which is 144, plus I sine 4 pi by 5. If I substitute k as 3, I'll get cos of 6 pi by 5 plus I sine of 6 pi by 5. And I substitute k as 4, I'll get 8 pi by 5 and so on. Where do you think the numbers are lying? They are now on a pentagon. All on the unit circle. Again, the pentagon is inscribed in a unit circle with radius 1, but the angles are different. The angles are 0, then 2 pi by 5, 4 pi by 5, 6 pi by 5, 8 pi by 5, and so on. So all the roots of unity are the vertices. So what is the geometric significance? Are the vertices of regular polygons inscribed in a circle. Inscribed in a circle. The radius is 1. Can I have radius something else? Yes, if it was a number r e raised to I theta. So instead of unity, if I had a number z as this, the radius is not unity, it is r, then any power will be same, the method will be same as what we did for unity. The angle will be divided like this. Correct? So that's the meaning of roots and powers of complex numbers. You will write a complex number always in the form of magnitude and angle and then use de Moivre's theorem to find powers and roots. And what is the significance? Well, they all lie on a circle with radius r. Okay. Now let's look at a simple example. If z is 2 e raised to I theta. Okay. Let's look at what happens to the power of z. So z square, it will become 4 e power I 2 theta. If z cube, it will become 8 e power I 3 theta. Z raised to 4, 16 e power I raised to 4 theta. Let's try to graph it and see how does it look. So z is some r e raised to I theta, so 2 e raised to I theta. So it's on the radius of 2 at an angle of theta. So 2 e raised to I theta. As soon as I square it, if it was raised to 0, where will it come? It will come to 1. Here it will come. If it is raised to 0. As soon as I square it, I get 4. So the radius increases, the modulus increases, and angle becomes double. Say for example, it was here. So it became 2 theta now, and the modulus became 4. So 4 e raised to I 2 theta. As soon as I cube it, it becomes even bigger, 8, and the angle becomes 3 theta. So e is to 3 theta. When I raise it to 4, it becomes even bigger, 16, and if I join all these points, what do you think the shape will be? As the power goes on increasing, what will happen? What kind of a shape is that? It's not a circle because the radius is not the same, but it is moving in an angular fashion. Think of what kind of a shape will that give you. And now imagine that z is half e raised to I theta. And also look at one more thing is, look at the radius, the modulus. The modulus is 2, 4, 8, 16, all are growing in geometric progression. Look at the argument, theta, 2 theta, 3 theta, 4 theta, all of them are growing as arithmetic progression. And try to imagine what will the shape look like. Repeat the same thing with z equal to half e raised to I theta. So z square will become 1/4 e raised to I 2 theta. So angle has increased but modulus has become smaller. Z cube will be 1/8 e raised to I 3 theta. Z raised to 4 will become 1/16 e raised to I 4 theta. Now try to graph it and see. So I'll start with 1, then half e raised to I theta, so maybe somewhere there. Then 1/4 and so smaller, somewhere there. 1/8, maybe somewhere there. 1/16, maybe somewhere there, and so on. Now if I join the points, what kind of a shape will it form? So think about both these things, two things. If r e raised to I theta, if r is greater than 1, if I go on raising to power, what shape will I get? And if r is less than 1, I go on increasing the powers, what shape will I get? So that will help you understand the significance of complex numbers and their powers and roots. Again, to summarize, every complex number can be written in 3 forms. Cartesian form, where a is the real part and b is the imaginary part. Modulus of this complex number is the real part square plus imaginary part square. Argument of this complex number is tan inverse of b by a. So I can also represent a complex number in the polar form as r theta, which can also be written as r cos theta plus I sin theta. In short form, it is called cis theta. What is cis theta? Cos theta plus I sin theta. That is, it's a short way of saying r cis theta means r cos theta plus I sin theta. And the last form is the Euler's form, which is e raised to I. We also studied De Moivre's theorem, which says if z is raised to n, which means cos theta plus I sin theta is also raised to n, then according to De Moivre's theorem, this power becomes the multiple of the argument. Power becomes like this. And that is easy to see if we see it in the Euler's form. The indices get multiplied, so it's easier to see it this way. Okay. Using this De Moivre's theorem, we showed the roots of unity by writing 1 as a complex number. And we found the roots of unity to be the vertices of regular polygons inscribed in a unit circle. Now, this is something we want you to understand really well. So this is going to be useful in a lot of the identity questions in complex numbers when we prove that questions or mathematical induction with complex numbers.